Now that we have some understanding of what operationalization is and the different scales of measurement that are available, I want to move on to talk about something called measurement error. So, um, like when I was talking earlier about how no measure that you choose is going to be perfect, sometimes it might be just because you chose something that's inappropriate, or sometimes it might be just because there are different sources of inaccuracy or error in the way that you assess anything. So some of those different types of measurement error I have displayed up here, and I'll just talk through all these different things. So there can be error due to the individuals that you're measuring. Now, in some of the hard sciences, when you're just measuring like a liquid or something, um, there's not generally going to be that much difference between one beaker of hydrochloric acid and another one, right? But when you're measuring people and their reactions to things or their levels of a particular trait, there might be lots of different things that are going on that are influencing their responses or their behavior. Some of these things might be due to enduring individual differences, like traits, like they might be extroverted or open to new experiences. They might be liberal or conservative or very in tune to their social situations or feel more egalitarian or more authoritarian. All these reliable differences that individuals have from moment to moment is going to or are going to affect their responses on all sorts of different behaviors or paradigms that they are responding to. Transient things about people's states might also affect their responses to things. So traits, stable things that might affect their responses, and transient things like moods or feeling tired or hungry or excited or something. Those types of individual differences that are changing from moment to moment might also affect somebody's responses. So you can imagine, just hearing that you got into a graduate school that you are really interested in, or just hearing that you got a job that you really wanted. If you heard that news right before you're going to go participate in an experiment, your behavior and your responses might be different than if you just heard you missed out on that job or you didn't get into that school. So all sorts of things like that might affect people. So those are the types of errors that are due to the individual people in your studies. You also, though, have to think about errors due to the situation that you are measuring something in or the situation the person finds themselves in. So let's imagine you are, measuring something about people's math abilities, let's say, and you measure it in a laboratory and during the period of that study, there happens to be construction going on outside, and it's noisy and it's distracting. That might be error due to the situation that you are putting participants into. It's probably not a very good measure of people's math ability to have them distracted by noise. You want the scenario to be quiet and distraction free. So anything like that, anything about the situation that you're constructing, whether it's something you're doing or something going on in the environment, might be a source of error due to situations. Now, these sources of error from individuals and situations can interact with one another. So you can imagine that some people that maybe are more neurotic or more distractible in general, maybe that construction noise is more distracting for some people than for other people's. So you have the error due to the individuals, something about their personal traits, interacting with the error due to the situations. So there's something about that combination of person and situation that's leading to some kind of bad measurement for a particular group of people in a particular situation. This, for those of you that have taken social psychology or in my social psych class, this probably sounds very familiar, right? That to really understand things about people's behavior, we need to understand things about them and things about the situations that they're in. But not only that, how those things interact with one another and influence behavior. So, individual and situational things can interact, and there also is a type of error that comes just from the type of measurement that you're doing. So just by asking people about something, you are affecting their responses. And people being in a study, asking people to, hey, have a natural conversation with this other person in the laboratory. Well, how natural is it going to be, right? So something about the measurement itself might not really tap exactly what you want it to tap. Or if you are, asking people really awkward questions, trying to get an idea of their, like, I don't know, sexual preferences or things about their values that are really personal, they might not always want to share everything about those. And your questions might be awkward or intrusive in a way that doesn't allow you to measure them properly. And that's something about the measurement itself that's influencing people's reactions to them. Another distinction that we might want to think about that's not it it's not exactly the same as those distinctions that I just talked about, but a bigger one between random and systematic error. Random errors are things that literally randomly affect your measurement across a sample. Systematic errors are affecting all of your measurements in a consistent way. So what I mean by this, random error is, just kind of the fluctuation and noise that you see in your measurement. And these are things that you're generally not going to be able to account for. Things like, the daily experiences that people have had going into your study, or the random distribution of people's personality traits across the different groups that you're collecting data from. So those are things that you're not going to be able to rule out, and they're going to make your measurement less precise. Systematic error is consistent across your entire sample. So this is just bias in the way that you're measuring things. So most often, the systematic type of error in measurement is going to come from something about the measure itself, or sometimes about the situation in which you're doing the measuring. So in the construction, noise example, if every person's score is reduced on a math test because they're all distracted by the construction site, that is a systematic error in your measurement of their math ability. Systematic because it's affecting everyone the same. If it were random, it might be things, everybody's own ups and downs in their daily life affecting how much they're trying on the math test or something. That's going to be a random type of error, but if it's affecting everybody the same, it's systematic. Okay, two other very, very important concepts in measurement are reliability and validity. These are probably things that you've encountered before, but I know, even in my like undergrad days and honestly into my grad school days, these were kind of difficult concepts. So I think these are a bit hard to latch onto. There's a lot of different types of each of these that can make it a little difficult to feel confident about them. So I want to go through these ideas very carefully. I'll do reliability in this video, and then I'll do validity in a separate lecture video. So reliability and validity are important for any type of measurement. If you have a good measure of something, whether it's an attitude, feeling, behavior, whatever, they're going to be reliable and valid. Reliability has to do with consistency. If you're able to get the same scores over and over, that might give you an idea that you have some kind of consistency in your measurement. Somewhat separate from that idea of consistency, though, is how accurate it is. Because you can imagine having a very consistent measurement, but it might be off target, right? Validity has to do with how accurate or truthful your measurement is. So see how these two concepts are separable but related. The way that they are really related is a measure can be reliable without being valid. It can be consistent but just off the mark. But it can't be valid without being reliable. If you're not consistent, if your measurement is just all over the place, then how could it be accurate if it's never really getting into one spot, right? So you need reliability and you want validity also. Reliability has to be there in order for validity to be there. And there are different ways that we can conceptualize reliability, different ways that we can test whether we have that consistency in our measure. One very straightforward way to test reliability is something called test-retest reliability. That is exactly what it sounds like. You give a test to a group, like let's say, let's stick with the math ability example I've been using. You give a math test to a group, and later on you give them the same test, maybe a week later, so they don't, remember all the questions or something. And then you do a correlation, just a relationship test between the first time you administered it and the second time. This will give you a coefficient, a correlation coefficient that goes from -1 to +1. And the closer it is to +1, the more positively correlated those things are, and the more reliability you are judged to have them. But there are problems with this because if people are taking the same test over and over, they might remember the questions, or they might just be getting better naturally. So there might be, artificially high scores because they're remembering how they did, or artificially low scores because it's just they're overthinking it. And also, you have to do this twice. You can't just run it once. You need to bring people back and do the test again. So it requires 2 measurement periods to test this reliability. Another way you might do it that's kind of analogous is give 2 different forms of a test to the same group. I have here that you could do it at a later time. You could also do it at the same time for this one. But you give like form 1 of a test to people, and then you give form 2 of a test to people. And you see, you try to make those forms as consistent as possible and measuring the same thing. And then you correlate the scores from the first form to the second form, those parallel forms, parallel meaning they're measuring the same thing ideally, and you correlate them just like you would the same test, and try to see if you have a high correlation between those forms of the test. This has problems too, obviously. It still generally requires 2 measurement periods. It requires you to make 2 different forms of the same test, which is a lot more time and effort, and wording can make a whole big difference when you are measuring things. So the way you differ wording between those 2 different forms might end up mattering a whole lot. A kind of, I don't know, very similar to parallel forms reliability is something called split half reliability, where you take a test you already have, you give it to everybody, and you split it into 2 halves. Maybe you take the odd number questions and the even number questions and split them, or the first half of the test and the second half of the test. You take those halves, split half the test, and then correlate them together and see if you have something that's relatively close to 1. So if you, in this kind of crude graphic I have here, if you had a 6-item test, usually tests are going to be more items than 6 in psychology, but sometimes there are short forms like that. But you would randomly take items from, or 2 sets of items. So you see in this first split half, we have 1, 3, and 4 in the first half, and 2, 5, and 6 in the second half. You'd take the scores on those items, and you'd correlate them together for all the participants and see what you got overall. So this correlation coefficient we have here, 0.87, that is generally a very good score for reliability. Remember I said it's just a correlation. It's going from -1, negatively correlated, through 0 up to +1, and you want it to be closer to +1. Around the 0.8, 0.8, 0.85, or 0.9 range is kind of the sweet spot you're looking for. If you get more than that, that's great, but that doesn't happen very often. You might see articles sometimes that have reliability scores that are like 0.7 or even 0.6 or lower, and that's when you might start to be a little bit skeptical that they are doing proper measurement for what they're looking for. What this split half reliability measure amounts to is something that we call internal consistency, meaning just literally that the items within a scale are consistent with one another. The items within a scale, internal to a scale, are consistent with each other, that they're all measuring the same thing. You can imagine, like, if you threw in items here, some of them for openness to new experiences and some of them for conscientiousness, you're measuring 2 different things. You're not going to have a very high correlation, right? So you get a higher correlation by having items that are more similar and measuring something more consistent. But there are better ways that we might want to look at internal consistency. You generally are going to do that by looking at all of the items and their intercorrelations separately. So let's imagine we have this same 6-item test that I was talking about before. Instead of just splitting them in half and running a correlation, what people tend to do is run a bunch of different correlations and combine them together. So I know this is a bit complicated here, but what I have put up here is a correlation table, and it crosses all the items together. So all of this diagonal here, the correlation is 1 because it's the correlation of each item with itself. 1 and 1 correlated 1. 1 or 2 and 1, sorry, 2 and 2 correlated at 1, right? Everything correlated with itself is a perfect correlation. Down here, below the diagonal, is where you see correlations of the individual items with all the others. So this column is how 1 correlates with everything else. Correlates with item 2 at 0.89, with item 3 at 0.91, and so on. So you see all these correlations together. You see every item's correlation with every other one averaged, and then you take the average of that and combine them all together, and you see a 0.85. So it's a little different from that split half reliability because it's combining a lot more different things together there. Um, and this is how you construct a good scale and make sure that it's internally consistent. If you saw that one of these items had a really consistently low correlation, like maybe item 3, these correlations are in the 0.4 or 0.6 range or something, what you might do then is just drop that item entirely and run it again and see if everything hangs together a little better. Sometimes it's a single item or a couple items that are just bringing down all of your internal consistency. When you do this whole test and average all these correlations together, you call this correlation coefficient that's been combined your Cronbach's alpha, just after a researcher from decades ago named Cronbach. And it's just what we call that coefficient. Nothing special beyond that. One other type of reliability I want to mention before wrapping up is something called inter-rater reliability. This doesn't have to do with just like looking at scales and lists of questions and stuff. This is when you're actually looking at behavior, or you're coding something in, let's say, like essays or articles or something like that. Inter-rater reliability is simply having different raters, so inter meaning between raters, making judgments about the same thing. So maybe you have a study where you are looking at the behavior of children at a daycare when they have, let's say, an experienced teacher versus an inexperienced teacher. And you want to look at all these different things with how children are behaving, like their sociability and how friendly they're being, how much they're playing. You would ahead of time come up with very detailed ways of coding for sociability and quality of play. And then you would have different people watch the same videos or watch the same play action live, perhaps, and give their ratings about those different measures. Then you would correlate together those different ratings and get some kind of combined rating, like an alpha score for inter-rater reliability. Because you can imagine the raters, just like measurements and just like participants, have some kind of bias, right? No rater is perfect, but if you combine together lots of different trained raters, then you might, just like when you combine items in a scale, by combining raters, you're going to get a more accurate or at least less biased score. Okay, I'll take a break here and talk about validity in the next video.